Good morning, students. Hope you people are having a good time during this lockdown. Today, we are going to see an important topic called homology modeling. It is a very efficient application in the field of structural biology. So, let's go deep into this topic. So, before into the topic, let me hide myself so that you could concentrate more on the topic. Okay. So, before getting into the homology modeling, let's see about the experimental methods available for structure determination. There are three methods available so far. One is the X-ray diffraction method, the second one is the NMR method, and the final one, which is the most recent one and well advanced one, is the cryo-electron microscopy method. However, many research groups including our research group in the school of crystallography and biophysics, our focus is mainly on determining the structure of protein structures associated to many disease conditions. However, the biggest problem is you have to get the sequence first, and then once you got the sequence you need to purify the protein. Once you got purify the protein, then you need to go for the methodologies, experimental methods which I told, such as X-ray diffraction, NMR, and cryo-electron microscopy to get the data. And once you get the data, you need to use specific tools to analyze the data, and then you have to solve the structure. Finally you will get the structure. So it is a very difficult experiment because it needs lot of time and hard work to come up with a novel structure. Moreover, these methodologies are very difficult to carry out on some of the important protein structures such as membrane proteins, membrane transporters, and so on so. If you deals with a globular protein or a simple bacterial protein, it is of really of simple use. However, when it comes to the complex proteins, these methodologies are very difficult. The most chance of getting success is very limited. However, there is an important technique called homology modeling. When it comes to homology modeling, it has been graded into three types. One is the simple homology modeling, whereas the homologs, the similarity between the homologs will be of higher range. When it comes below the lower range, then there is a technique called threading, which models this protein of your sequence of interest based on the fold which has been reported in the fold recognition server. And also the third one is the ab initio methods, which is purely computational. The first one is more reliable than the remaining two because the remaining two methods such as threading and ab initio methods is quite complex, and this method works only when you have experimental data related to the protein that you are working on. So this is the flowchart of homology modeling. You could see when you start to work on homology modeling, the flowchart which I shows here should be kept in mind always. Otherwise, you may miss some methods, or you may end up in having a invalid model. Okay, the first thing that you need is a target sequence. So the target sequence is the sequence which you want to get the structure of the protein that you have. Okay, here the target sequence is the protein sequence because we are going to get the structure of the protein. So we are having a sequence that we are going to model is called the target sequence. Once you get the target sequence, you need to select the similar structures which has been reported in the PDB for your sequence. Since you doesn't have the structure, you are in search of a similar structures of your sequence. So that structures are called template structures. What is it? Template structures. So this kind of selection of templates can be achieved using a tool called BLAST, that is called Basic Local Alignment Search Tool. It is very simple. You just give your target sequence, that is so-called query sequence, and then it will search against the database. Since you are searching in search of a protein, you have to search against the protein database. It will report the list of template structures based on the sequence identity, sequence similarity, e-value, z-score. You could come up with the proper template for your modeling. So for suppose you are giving a sequence and it will report 10 to n number of templates. Okay, so you need to select templates based on the criterions which I showed, such as similarity, identity, e-value, z-score, and query coverage. So these factors are very important when you select the template of interest. The first factor is similarity and identity. If the similarity and identity goes higher, the selection of your template is is really good. If the similarity identity goes lesser, then the selected template is not of higher importance. So as the similarity is high, the selected templates will be of higher range. Likewise, there is an important factor called query coverage. Query coverage should also be higher. If your query coverage is less, though the template identity is high, then the template which you select may not be valid, because if you have a 100 residue, okay, in your sequence, if you have 100 residues, but the query coverage is only 20%, but the identity is 90%, then the template doesn't work, because the query coverage doesn't covers the entire protein of interest what you are looking for. Whereas if the query coverage is of 90% and the identity is 35 to 40%, then the template is valid, so that you could come up with the model. So on these kind of criterions, you should select whether your template is correct or not. Before selecting the templates, these criterion should always be followed, so that you will get a very valid model. Next thing is, once you got to see the template hits, you need to select whether you are going to do single template modeling or multi-template modeling. If you select only one template, then that is called single template modeling. If you select multiple templates, then you call multiple template modeling. Nowadays, the researchers advise the people to go for multi-template modeling. There are so many papers which has been published recently stressing the importance of multiple template models, because since this is a concept is based on homologs, when you do modeling based on multiple homologs, then the predicted model will be of higher value. This is what the researchers feel, and they always stress the students to go for multiple template modeling. So once you got the templates, you need to align the target sequence with the template structures, because this is a very important step in homology modeling. Because we feel that the sequence of your query, that is called the target sequence, is matched with the sequence of the template structure. So based on the homology and identity, the predictability of the predictability of the target structure will be of higher value. So you could see here, right, there is a simple alignment, target template alignment, something like that. Likewise, you could see an alignment for your sequence with the template structure. Since it is this flowchart is based on single template modeling, you could see only one template. But whereas when you go it for multiple template modeling, you could see 2 to 3 templates in general. So once you got the things to be aligned, then you need to build the model. So what it does is, by replacing the amino acids of the template structures, by replacing the amino acids of the template structure with the amino acids of your target sequence, the fold will be retained, whereas the amino acids will be replaced based on the similarity and identity. This is the funda. So what it does is, it takes the amino acids from the structure, and it will replace your amino acids wherever it is wherever it has been aligned, and it has been replaced with your query sequence. Once this process has been done, then you will get a model that is called final model, which is called the target model. So you could see the template structure and the target model is almost the same, right? The only problem is it has been replaced by what? Your residues. So the template structure has some kind of residues, whereas these residues has been replaced by your target sequences, so that you could see the model which has been generated by you is almost the same as the model which has been associated with the template structures. Because this is the concept. Based on the homologs, the sequence of your subject, that is called the query sequence, has been modeled based on a certain criterion called alignment parameters, and once the alignment parameters got satisfied, it has been modeled. This concept is called what? Homology modeling. It looks very simple thing, but you need to understand the criterion for selecting the templates. Once you fail to do so, the model which you get will not be a valid one. So those who want to work on this technique should always keep in mind about the selection of template structures. As the name pronounced, homology modeling based on the homologs, based on the common family, based on the ancestral origin. So this is the concept. For an example, it is very easy to understand that the homology modeling is purely based on the homolog, purely based on the ancestral origin. Okay, so we all know that the central dogma, right? DNA to RNA, RNA to protein. Whereas the central dogma of bioinformatics is similar sequence, similar structure, similar function. So understanding this common consortium, we could predict the model based on the technical homology modeling in a considerably valid way. So the central dogma of bioinformatics is similar sequence, similar structure, similar function. So likewise, the one which we have, that is called the target sequence, is supposed to be similar with the template structures. Since the sequence is similar to the sequence of the template structures, we could predict the structure of the target sequence, assuming that similar sequence is supposed to have similar structure and it's supposed to produce similar function. This is the concept of homology modeling. Since you people are beginners into this, I think this kind of a valid explanation will help you to come up with the homology model for your project. However, I want you to read so many research papers related to the homology modeling. Okay, moreover, you need to do this manually and also using online servers. I will explain about this in the later slides. Okay, next you got the model, right? Finally you got the target model, right? Once you got the model, you need to validate whether your model is good or not. If it is yes, if your model is okay, then you shall say, oh, yeah, I got the model. If the model is not good, your model is not well characterized, then you need to start again. So this is the protocol that you have to follow to come up with the model. So there are certain criterions to check the validity of the model, such as ProCheck, WhatF, ProSA, verify. There are so many online servers to verify the validity of the model. However, the important concept to validate your model is Ramachandran plot. So you all know that Ramachandran plot is a very important tool to check the stereochemical parameters of the amino acids, so that if it fits into the plot, then your model is valid. If it doesn't, the model is not valid. In general, you could see there are 4 regions: most favored regions, additionally generously allowed region, additionally allowed region, and disallowed region. Your amino acids which has been modeled should fall onto these regions, otherwise the model may not be valid. You could see here, this is the Ramachandran plot of a very good template structure, in general X-ray structure. Whereas you could see the NMR structure, the Ramachandran plot of NMR structure is not that much of good data. It looks chaotic, right? Whereas the X-ray structure here, it looks really fine. Whereas you could see the NMR structure, you could see so many residues in the in the disallowed regions. Here in general, this is called most favored, generously allowed, additionally allowed, and then these regions are called disallowed regions. So this is the concept. Whenever you could see residues in the disallowed region, it's your responsibility to bring those residues in the at least in the additional allowed region. You have to make sure why. What is the reason for those residues being outside? Is it possible to bring those residues inside the Ramachandran plot? Is the residues which are outside, which are in the disallowed region are of higher importance? You could always pay attention and focus the residues of importance. If it is of important, if the residues which lies in the disallowed region are of highly important, then you need to pay attention to make it into the any regions, or so otherwise your model may not be valid. So these, as I told, These are all some of the prediction servers that you could see, like a Swiss model, 3D Jigsaw, CPH, so on, so on, so on, so. You shall just submit your sequence, whatever the steps that I have explained, it will report. However, the being a structural biologist, you have to do things on your own. I always prefer manual modeling is the best thing rather than doing things online. Okay, so what are the steps involved in manual modeling? Very simple. You need to have your sequence. How you will get the sequence? You will get the sequence from any sequence repository, the like Uniprot, NCBI, GenBank, and so on, so on, so on. Okay, you have to take your sequence. That is your raw sequence. That is called target sequence. Once you got the sequence, you need to use an important server called Blast. Just go to Blast, paste your sequence, and then there will be a database you have to search. That database is called PDB, protein data bank, because you are in search of, your objective is in search of templates. Okay, right? So once you once you give PDB, and then there will be multiple blast options such as pblast. Since you are doing protein blast, you have to do pblast, and within pblast there are two options, pi blast and psi blast. Position specific iteration, pattern initiation. So based on your object, you have to select one, and it will give some kind of a results. So once you got the results, you could see on top of it there is an important thing called family. So that determines the family of your sequence. So it determines the homology of your sequence. It gives the homolog or ancestral origin of the sequence. Based on this ancestral origin, it will report the list of template structures. So you need to select your templates wisely. As I told you before, the selection of templates should be wise based on the criterion such as e-value, z-score, query coverage, similarity, and identity. So once you select the template, you need to make sure manually you have to write that the template structures that you are selected. So once you got to know about the template structure is what? The name of the PDB IDs, right? You have to make a note of this PDB IDs. Then you need to go to the database called PDB, use those PDB IDs, get the structures of this database, and try to superimpose using PyMol and see how the architecture of the protein looks like. So once you got the overall architecture of the protein, then you could come to a conclusion. Yeah, this is what the fold of your query sequence. So based on these assumptions, you shall submit your sequence to these online softwares, and then you shall always compare your results with the model produced by these kind of online servers with the manual modeling. These kind of things will always get you to with the final validated model. So once you got the model, you need to validate with the protein server called Ramachandran plot, or so and so and so, and then you shall do it further for your research proceedings. I hope you understood. Thank you so much. Thanks for your time and effort.